Hi, I'm Navid. I'll be talking about a work we've submitted with my co-authors listed below and should be appearing soon in the Journal of Fluid Mechanics. The subject is essentially how linear mechanisms contribute in sustaining wall turbulence. So we know that in wall-bounded flows, turbulence is sustained via an intimate interaction between coherent structures like the rolls, the streaks, the mean flow shear, and turbulent fluctuations. And these interactions come about into what's been called the self-sustaining cycle. And an outstanding question that's been hanging around the past few years is how is energy transported from the time-dependent streak back to the fluctuations to close this cycle. This is something that I'll try to address today. So several theories has been proposed, several mechanisms has been proposed for how energy is transferred from the streak back to the turbulent fluctuations. This involved the model instabilities of the streak flow, transient growth due to the non-normality of the linear dynamics, neutral modes and wave vortex interactions, or parametric instabilities of the time-dependent streak, among others. So the way we will, let's set the scene. So we start with the incompressible Navier-Stokes equations. And what we will do is something that will at first may seem ad hoc, but let's decompose our flow into a base flow that we will call capital U, and fluctuations, anything other than our base flow. And in this particular work, we will take our base flow just to be the streamwise mean of the streamwise component of the velocity. So anything else will call it fluctuations. Now, doing so, we can rewrite our Navier-Stokes equations as two equations, one for the evolution of the base flow and one for the evolution of the fluctuations. And note that here our base flow has, it varies in the cross stream, it varies in the spanwise direction, it also has, it fluctuates in time. So the only thing that we've done is that we averaged in the streamwise direction. Now, the fluctuation equation can be written as shown below, and it involves two parts. It involves a part which has a linear operator that depends only on the base flow itself, and some other part which is quadratic in the fluctuations. And this is what we will be calling nonlinear processes. So, two remarks. Now here, when I decompose my flow, I didn't linearize about any solution of the Navier-Stokes equation. I just ad hoc selected something that I call my base flow, and this base flow has a streak component. It has some spanwise variation, and this will be important. And I just decompose my flow and call linear dynamics anything that is included in this process here, which is the linear operator that depends on the base flow and acting on the turbulent fluctuations. Another thing to note is that if we've chosen our base flow differently, a process that can be included in the linear dynamics here could be as well transferred in the nonlinear part. So what I call linear processes, it is a function of the choice for what my base flow is. So the numerical setup of how we will try to tackle our question of what's the main processes underlying the energy transfer from the streak to the fluctuation is the following. We'll use a minimal flow channel, a constant pressure gradient channel, and at Reynolds number tau around 180. And we know that this This is a minimal channel, so it sustains turbulence. Here's the time series of the turbulent kinetic energy, and the phase diagram of the turbulent production versus turbulent dissipation. What we do is that we run the simulation for very, very long, and we save all snapshots of what we call base flow, so that we can analyze them later. We can use them for interrogating our output. So there's two ways to assess the various mechanisms proposed in the literature that come into play. The first method is to interrogate output from the direct numerical simulation. This has the advantage that it's a non-intrusive method, and but it cannot provide us with causal relationships. The other method is to go and sensibly modify the equations of motions in the minimal manner possible, so that to preclude some of the mechanisms you're trying to question, and then look at the output of those modified equations. And so this is an intrusive way of attacking the problem, but it allows us to infer causal relationships, which mechanisms are more important than others. So let's start by first asking the question, are model instabilities of the streaky flow important for sustaining turbulence? So what do we mean by model instabilities of the streaky flow? At any point, we have our base flow, we can have a snapshot of our base flow, what we call a base flow, and which involves spanwise variation. So it has a streak component in it. And we can take our linear operator, the linear operator which was involved in the linear part of the fluctuation dynamics, and decompose it, do an eigen decomposition of that. So here we see the eigenvectors and the inverse of the matrix of the eigenvectors on the right, and we have a diagonal matrix with all the eigenvalues. So if any of these eigenvalues has a real part which is positive, this means instability of the streaky flow. And if we do play this game in the direct numerical simulation, we have all the snapshots of the base flow. We've saved all the snapshots at every time step. So we go and we do this eigen analysis at every time step. We see that most of the times, or almost all the times, the flow is unstable. This is the largest growth rate that we find in the flow. And usually there are 2 or 3 unstable eigenmodes at every time instance. Now, what's also noteworthy is that if you go and compute the autocorrelation of the base flow, we find that the base flow changes at least 3 times slower than the typical e-folding time of these instabilities. So in principle, not only the flow is unstable, but these instabilities have the potential to grow and affect the fluctuations. Okay, this is what we get by just interrogating the output. Now, if in fact these model instabilities are crucial for the self-sustaining cycle, it means that if we take them out of the game, then the flow should laminarize. So what we do is now we go again, and at every time instance, we do an eigen decomposition of the linear operator, and we check whichever modes are unstable, whichever modes have eigenvalues with positive growth rates, we go and make these growth rates negative. So if, for example, if in this case, only mode 1 and mode 2 were unstable, we go and put a minus in front of the growth rates. We don't change anything else, the structure of the eigenmodes, nothing else is changed. We compose back the linear operator, and we denote it with a tilde on the top, just to remind ourselves that this is a stabilized version of the linear operator. And now we can run Navier-Stokes again with only this slight modification, that at every time instance, if our base flow corresponded to a linear operator which had 2 or 3 unstable eigenmodes, these unstable eigenmodes were rendered stable by changing the sign of the growth rate of the eigenvalue, nothing else. So we do that, and we see that, of course, then in this case, there's no instabilities by construction, but the flow still is turbulent. So if we see the time series, a slice of the time series of the turbulent kinetic energy, there's still turbulence in the flow. And we see the turbulence production dissipation diagram. It looks more or less like before. And not only the flow is turbulent, but with more or less the same statistics. So here we see with dash the turbulence statistics from the direct numerical simulations without any modification, and with solid lines the same statistics from our stabilized direct numerical simulations. So the only difference, removing the modal instabilities, is that we see that the turbulence intensity is dropped by around 10%. But other than that, the flow remained turbulent and looked as turbulent as before. So with that, we conclude that modal instabilities are not crucial for the self-sustaining cycle. And what was another important thing to note here is that interrogating the output did not provide us with these conclusions, because just from interrogating the output, we saw that modal instabilities were there, and we saw that they had the potential to be important, but it was only when we did this causal, sensibly modifying the equations of motion and seeing what the output is, that we were able to make this causal relationship about modal instabilities not being important. So next, we want to understand if non-modal transient growth is important for closing the loop in the self-sustaining cycle. So non-modal transient growth refers to energy amplification or perturbation amplification if you have a linear system at any finite time horizon, and it can be quantified by the maximum energy gain you can get over a time interval capital T, denoted here. And it's just the maximum over all initial conditions of the energy of the fluctuations of time after time capital T, after the initial time. So one would say, though, but how are you sure that if you see an energy growth, it's because of the non-normality of the linear operator, and it's not because of any modal instabilities? And that's true. So to make sure that to make sure that we really assess how non-modal transient growth due to the non-normality of the operator comes about, we will use the stabilized version of the operator. So if we do the same analysis on the stabilized linear operator, and we see energy growth at finite time horizons, it means that this energy growth did not come from any instabilities, because there were none, but it came about because of the non-normality of the operator. So we compute now here this maximum energy growth with tilde to remind us that it's from the stabilized linear operator for various base flows that we've saved. Remember, we've saved the base flow for every time step of our simulation, so we can take all of them and compute their energy gain as a function of this capital T, of this time horizon. And here's the plot on the left. How much is this energy gain for all this ensemble of frozen base flows that we've saved as a function of the optimization time? We see that there's a sweet spot at some point for optimization time around 0.35. The base flows show the most energy gain, which is of order 100. What you see here with gray is the spread of all the various energy gains we obtain from all the various base flows that we have saved. And with the black line, you just see the sample mean of all of this. And it's important to note that we get energy amplifications of the order of 100. And that to come about, it's important to compare with the same energy amplifications that come about when we use as a base flow the time mean and span-wise mean and stream-wise means, just the mean flow shear, which varies only the cross-stream direction. In that case, we get energy gains of order of 10. So the span-wise variation, the streaky part of the base flow, is what allows us, or what seems to allows us, to get energy gains of an order of magnitude more. Now, this is what we get when we check about energy gains for every fixed frozen snapshot of our base flow. What if we allow the base flow to vary in time? We put the whole time series and we can do the same calculation. And what we find is the following. Now with red is what we had before with the frozen snapshots, and with black is what we find the energy amplifications we gain when we put the full time varying base flow. And we see that for short times, more or less, there's no change. So the time varying base flow gives us the same energy amplification as the ensample mean of all the various frozen snapshots we had before. Now, this is just from interrogating the output of the DNS, or modifying it slightly just to make sure we are not confusing here energy growth due to non-normality and energy growth due to linear instabilities. But the real question is, okay, is this non-normal energy gain enough to sustain turbulence? So what we do here is that we go back to our fluctuation dynamics, and we run again these simulations, just the fluctuation dynamics, using the stabilized linear operator and using only a snapshot, a frozen snapshot of our base flow. Remember, we have a lot of base flows that we've saved, so we put all of them. We put a series of them, and each time we run the simulation and we ask, does it sustain, does it remain turbulence, or does it laminarize? So most of the times, turbulence persists. Around 80% of the simulations we did, and we did more than 500 simulations. 80% of the time, turbulence persists, and when it persists, it looks and feels as turbulent as before. This is just the turbulent production dissipation diagram from a case that it persisted. Now, what's interesting to ask is, so what made this? What differentiate between these base flows? Which base flows were able to sustain turbulence? And to do that, we plot here on the horizontal axis the maximum energy gain for each of these frozen snapshots of the base flow, and on the vertical axis, the mean turbulent kinetic energy that they managed to sustain. So if the flow laminarized, the mean kinetic energy is 0. So we see that if the base flow had an energy gain which was greater than around 40, then it was able to sustain turbulence. Okay, so this number 40, of course, is not something, we don't expect this to be some universal number, but it's dependence on the Reynolds number that we had here. So in a higher Reynolds number, this number could be different. This minimum critical energy gain that we need to sustain turbulence just only via transient growth mechanism could be different. Now, the question that arises is, okay, what was different between these base flows that were able to sustain turbulence and just through non-normality, just through non-modal amplification, and and the base flows which were not able, and in which case the turbulence laminarized. So here I show you six snapshots of the base flows we've used. On the top, you see three of them that were able to sustain turbulence, and on the bottom, three of them that they resulted in laminarization. And just from first glance, what you can see is that their main difference is the spanwise shear that they have, that those who were able to sustain turbulence had a much stronger spanwise shear and spanwise variation, which resulted in much higher energy amplification due to non-normality. And here I'm just presenting you this optical evidence, but if you go and read our paper, and we have made a lot of detailed experiments to quantify how the spanwise shear is crucial for producing non-normal energy gain and sustaining the turbulent flow. So in summary, we've seen that modal instabilities of the streak are not crucial for the self-sustaining cycle. They do matter. Removing them resulted in 10% of reduction in turbulence intensities, but it did not change the qualitative picture of the flow. So if one asks, how does energy goes from the mean flow back to the perturbations, back to the fluctuations? One simple answer is via transient growth. This is what our experiments seem to suggest. And what produces this transient growth? Mostly the spanwise shear of the base flow. So the streaky component of the base flow is what is crucial for producing transient growth and energy amplification through non-normality. And for a thorough discussion on this, I'd urge you to have a look at the paper. And what else we found, and I haven't discussed this much, is that the time variability of the streak doesn't seem to enhance the energy transfer to the fluctuation, but it does allow the flow to sample all these independent transient growth events, resulting to the actual observed statistics. Remember when we asked about what was the energy gain from a time mean varying flow, we found exactly that it was exactly the same gain as from the sample average from all different frozen snapshots of our base flow. And more of this in the paper. So in summary, realistic world turbulence can be exclusively supported by transient growth. And with that, I'll stop and leave room for questions. This is just pretending that a lot of people are here. See you.